7.5 exponential functions. Here, I want to change the color back to black here. Exponential functions. Okay, it's a very important function. Why? Because it has a lot more flexibility and subtlety to it than a linear function. And so we can describe a lot more things in the real world. So it has the form, as it says right here, a times b to the x. A is the starting point, b is the rate of change, and then x tells you how many times the rate of change is applied to a. So a, starting point, b, rate of change, x, as an exponent, tells you how many times the rate of change is applied to b. So, say b, you have, let's look at y equals 2/3, 2 times 3 to the x. Okay, so I have a little example here. Y equals 2 times 3 to the x. Okay, so a is 2 and b is 3. Now, as a rate of change, it's 300%. So if x equals 2, then this would be y equals 2 times 3 times 3. Okay? 18. And so on. Okay? Now, if it was, and then to the third, if x equals, this is if x equals 2, if x equaled 3, then would be y equals 2 times 3 cubed, which would equal 2 times 3 times 3 times 3, or 54. 2 times 27, 54. Okay, so that's how it works. It's really, really handy function. Now, let's look at y equals 4x. A equals 1. Now, here's an interesting thing. If x equals, what about if x equals 0? Then y would equal 1 times 4 to the 0. 4 to the 0 is 1, so y would equal 1. And so A is the starting point. It's the y-intercept. A equals y-intercept. Okay, so let's look at the third example. Y equals parenthesis 1/2 to the x, quantity 1/2 to the x. A equals 1 again. So 1/2 to the x, the y-intercept, 1/2 to the 0. So when x equals 0, that's the y-intercept. Then it's going to be a will equal 1. A equals 1, so the y-intercept is going to equal 1. It'll be 1 times 1/2 to the 0, which is 1. Okay, and now I got to stop and insert some pages, or pause. Okay, now I'm all set. So we got example 1. Graph A is greater than 0 and B is greater than 1. B, by the way, can never be negative. And if you think about it, you're going to see why. The graph would not be continuous, because if B were negative, it would be constantly changing from negative to positive. All right, so exercise 1, example 1, graph with A is greater than 0, B is greater than 1. Y, now we're going to graph, they're going to graph y equals 3 to the x. Okay, now you see the table. A is 1. Here's our model. Y equals A times B to the x. A equals 1. It's 1 times 3 to the x. And B equals 3. Okay, the y-intercept. A is the y-intercept. So the y-intercept equals 1. Now, let's look at the graph, the way it behaves. As x approaches negative infinity, y is going to approach 0. It's going to approach it but never reach it. So the left-hand side of the graph, the left arrow over here, that's an asymptote. Okay? And as x approaches I don't know why it does this sometimes. As x approaches positive infinity, y approaches positive infinity. Okay, and you can see this clearly in the behavior of the graph. Okay, so when x is negative 2, 3 to the x is 3 to the negative 2, which is 1/9. When x is negative 1, y is 3 to the negative 1, which is 1/3. When x is 0, y is going to be 1 times 3 to the 0, which is 1. There's the y-intercept right there, and so on. So, and then when it's to the 1/2, they take the square root of 3, which is 1.73. I don't know why they bother putting that on. And then 1/3 to the first is 3. So you can see 1, 3, and then 2, 9 up here. Okay. So y-intercept equals 1. Domain. All reals. X goes forever to the left and forever to the right. And the range, y is greater than 0. Okay, y goes up forever, and it approaches but never reaches 0. Okay. So, guided practice. Here we go. GP1. Graph y equals 7 to the x. Okay? To the x. So, a equals 1. So that's the y-intercept. B equals 7. That's the rate of growth, 700%. Okay. And so we can see the domain is going to be all reals, and the range is going to be y is greater than 0. Okay. So let's get some graph paper on here. And we'll put that down. Okay. Now I'm going to modify this graph paper a little bit, and so when you're working on this, that looks a lot big enough, because we won't have any negative values. So I'm just going to cut out the negative part of the graph. All right, and so let's make a table here. Now the table this is going to be hard to graph. Here's x and y. So let's say when x is negative 1/3, negative 3 I should say, when x is negative 3, y will equal 7 to the negative 3, which we won't even bother. That's 1 over, that's going to be 1 over what? 7 sevens are 49 times 7. What is that? 49 times 7. I think it's 213. 7 times 9 is 63. 4 sevens are 28. Yes, that's it, 343. I can never remember that one. Okay, so that's going to be 1 over 343. That is very hard to graph. Okay, when it's negative 2, it's going to be 1 over 49. And when it's negative 1, it'll be 1/7. And when it's 0, it'll be 1. And when it's 1, it'll be 7. And 2, it's going to be 49. So how the heck are we going to graph that? It's very hard. So you got to really play with the scales here because you're going from really small numbers, 1 over 343, to really big numbers, 49. So anyway, we'll take a stab at it. We'll graph -1. So here's -1, and that'll be 1/7. And 0 is 1. And 1 is 7. 1, 2, 3, 4, 5, 6, 7. And there we go. And that's just about the best we can do. We got 3 points, and we can see how this thing is going. We put the arrows on the end, and that's it. That's about all we can do, doing it by hand. We're not going to do it by calculator right now. Okay? So that's guided practice number 1. And I just want to stop for a second and look at here. Let me pause this. Now another way we could write the range instead of all y such that y is greater than 0. You could write it like that as well using set notation. Why don't you do that? Okay, so that's a guided practice, and that's correct. Now, let's move on. Functions of the form y equals ab to the x, where a is greater than 0 and b is greater than 1, are called exponential growth. You can see exponential growth. It zooms up really fast. Now, where the absolute value of b is less than 1, where b is less than 1 and greater than 0, called exponential decay functions, and also have the same general shape, only it's reversed, if you will. Okay? For obvious reasons, the negative exponents are going to make y big. So let's look at this example right here. Y equals 1/3 of the x. Okay, a is 1. B is 1/3. So when x is -2, we're going to have 1/3 of the -2, which is 1/3 to the -2 equals 1 over 3 to the -2. 1 to the -2, which is simply 1, over 3 to the -2, which equals 1 over 3 to the -2, which equals 3 squared over 1, which is 9. Okay, so when x is -2, it starts out, it's really big on the left, and then it's as so. You can see what it's doing. As x approaches -infinity, y approaches positive infinity, and as x approaches positive infinity, y approaches 0. That's when you have exponential decay. And the y-intercept is 1 because a is 1. Okay? And the domain and range are the same. No change. Domain is all real numbers, and the range is the set of all y such that y is greater than 0. Okay, that's that. Guided practice. Okay, here is GP2, and we're going to graph y equals 1/2 to the x. Okay, now we got a little bit of a wrinkle here. Okay, this number, this -1, let's look at the form of the graph. Y equals ab to the x plus c. Okay, c is going to be heavily involved in the range. And the range is the set of all y such that y is greater than c, whatever c is. Okay, so this number is, you compute ab to the x, and then you add c to it, whether c is positive or negative. So C is going to determine the low end of the range. Unless A is negative. And that's another case. We haven't come to that yet. All right, so anyway, let's make this graph here. Okay. So let's here I'm going to put the graph in here. I have to do this and then do this, and then hopefully I can put this graph in. Okay. And I'm going to make it a little bigger. And again, I'm going to cut off the bottom end of the graph because we don't need it. Okay, and let's make a table right here. So we have X and Y. Now, B is 1/2. So if X is, say, -3, then Y is going to be 1/2 to the -3, which will be 1/2 to the -3, which is 2 cubed over 1, which is 8. And if Y is -2, then if X is -2, then Y will be 4. And if X is -1, then Y will be 2. And if X is 0, Y will be 1. If X is 1, Y will be 1/2. And if X is 2, it'll be 1/4. And 3, it'll be 1/8. Okay, so I go to -3, and it's 8. 1, 2, 3, 4, 5, 6, 7, 8. I'll put that in. Okay, -2, it's 4. 1, 2, 3, 4. And at -1, it's 2. And at 0, it's 1. And at 1, it's 1/2. And then 1/4, and then 1/8. And here's our graph. Okay, headed toward the... Okay. And that's that. All right. And I'm just going to double check this guided practice here. Okay. All right. So let's go to the next page, I think, where they got this whole thing here. Okay, key features of exponential functions summarized as follows. Okay, a b to the x, they've got exponential growth and exponential decay. The difference between them, for exponential growth, b is greater than 1. For exponential decay, b is less than 1 and greater than 0. Okay, and then we have all kinds of real-world examples, tons and tons of them that use this. Okay, now this is solved with a calculator, so let's take a look at this, and we'll do this on the calculator. And it would be a really good thing for you to bring a graphing calculator to class to go over this. All right. So the function c equals 179, that's a, times 1.029, that's b, that's the rate of growth. Okay, so c, it's rather small, it's 2.9%. But the rate of growth is greater than 1. Okay, so this is exponential growth to the t. Okay, so we, instead of having y, we have c. Instead of having x, we have t. Otherwise, I mean, there's no difference. Okay, graph the function. What values of c and t are meaningful in the context of the problem? Well, we got the graph here. T represents time, so the only value of t that makes any difference is t is greater than 0. And at t equals 0, the consumption is 179, because 1.029 to the 0 is 1. So we got 179 times 1. So 179 billion liters. Okay, so in the context of this problem, c greater than 179 is meaningful. And obviously, t greater than 0 is meaningful. All right, So how much soda was consumed in 2005? So that'll be B. Okay, how much consumed in 2005? Well, you plug in 5 for T. 179 times 1.029 to the 5. Now let's go over how you do that on the calculator. So let me swing this over here. 179 times 1.029, and then up arrow, that's the exponential, and then 5. Okay, 179 times 1.029 to the 5th, hit enter, and you get 206.5, approximately. Okay, so world soda consumption in 2005 was approximately 206.5 billion liters. My God, it's a lot of soda. Okay, guided practice. Biology, certain bacteria population doubles every 20 minutes. Okay, doubles every 20 minutes. That's not good. Well, unless a lot of good bacteria. Most bacteria is good. Only a few bacteria are bad. Okay, beginning with 10 cells in a culture, the population can be represented by the function B. B is how many bacteria there are. We're having that instead of Y. Equals 10. That's the starting point. Okay, that's A. Times 2, that's rate of growth. It doubles. That's the rate of growth. That's B. To the T. T is increment of time in 20 minutes. How many will there be after 2 hours? Okay, well, 2 hours, 60 divided by 20 equals 3. So in 2 hours, you're going to have 6 intervals. So T will equal 6. So we don't have to graph this. This is pretty easy. So B will equal 10 times 2 to the 6th. Now, everybody knows that 2 to the 6th equals 64. So this should be, B should equal 640 after 2 hours. Now let's see if I got this right. I'm going to check my guided practice here. Yep, 640 it is. Okay, it's real handy to know these powers of 2. They can save you a lot of time. Okay, identify exponential behavior. Recall from lesson 3.3, the linear functions have a constant rate of change. Okay, y equals mx plus b. M is the rate of change, and it's a constant. It's a fixed number. It doesn't change. Okay. Now, and then x, that rate of change multiplies the input x. All right. Now, whereas with exponential functions, y equals a b to the x, we have a constant rate of growth. Okay? So, we're not taking a and multiplying it by some fixed number. Instead, we're multiplying it by a rate. Okay? It's two very different things. M is a rate, okay, but this is a ratio of growth, and x is the number of times that we apply it. So instead of having m times x, where x is the input and we multiply it times m, we take b and raise it to the x power. So we're multiplying it. So this would be the equivalent of m times m times m to the x power. Very different, okay? And a much faster and nonlinear rate of growth. Okay, so let me erase all this. Okay, so let's go on and do the example. I believe it's on the next page. Example 2. Example 4. Okay. Identify exponential behavior. Now we look at this table. X increases by 5s, but what's y doing? Y is not changing by a set amount, but it's changing by a ratio. 64 over 32 cuts in half. 32 over 16 cuts in half. 8 over 4 cuts in half. So the ratio of change is 1/2. 1/2, 1/2. There's a constant ratio of change And so that's exponential. In this case, it's exponential decay. All right. So that's one way to find it. All right. Then method 2 is to graph the points and see if it looks exponential decay in this case. So you could do that starting at 64 and then down to 2. Okay. Now, guided practice number 4. Determine whether the set of data shown displays exponential behavior, right? Yes or no? Yes or no? Explain why or why not. Okay. X is increasing by 3s. 3, 6, 9, 12, 15. Y, as X increases by a steady rate, by 3s, Y is increasing not by a fixed ratio, but by a fixed amount, 4, 4, 4, 4, 4, 4. And if we graph this, it would be a straight line. So, how are we going to answer this? Y changes by 4, a fixed amount, not by a fixed ratio. And what equation describes this? Well, what's the y-intercept? 12. And what's the rate of change? Okay, when y changes 4, x changes 3. So y equals 4/3 x plus 12 is the equation. And if you plug in 0, it's going to work. If you plug in 3, it's going to work. If you plug in 6, it's going to work. If you plug in 9, it's going to work. If you plug in 12, it's going to work. Okay? All right. Moving on. And that's it. We are finished. Okay, and you're ready to start the homework. Okay.